Welcome all to today's lecture. Myself, Assistant Professor Tuku, and I am presenting my lectures for the subject Microprocessor and Microcontroller. Subject code KEC 502, and this subject is being taught in 5th semester. So today, I am going to discuss the interfacing peripheral devices with 8051. So let's see that how this is done. So here we are talking about the memories. As we all know that external ROM is meant for storing the program or data. ROM is a type of non-volatile memory. Data is not lost even if the power supply to the IC is taken off. ROM can be classified into ROM, EEPROM. PROM is programmable ROM. EEPROM is electrically programmable ROM. Erasable programmable ROM. EEPROM is electrically erasable programmable ROM. Next is flash EEPROM. Last is mask ROM. So all these ROMs are fabricated using different technology, and hence the name define them. External addressable ROM for 8051 is divided into two parts: program code space and data memory space. So ROM can be used for both, for storing the code and for storing the data as well. To access the program space, we require a program counter, that is PC. It locates and fetches the instructions. So we use the instruction move C A, @A plus DPTR instruction to get the data, where C stands for code, and it is 64 kilobytes in size. Now, how to access program space? For storing the program code, we can either use on-chip ROM or off-chip ROM, or a combination of both on-chip and off-chip ROM, depending on the status of EA pin, that is the external access pin. Internal program memory, that is 4 kilobytes, and it ranges from this to this, plus external program memory, which is of 60 kilobyte, and it ranges from this to this. We can select this mode by making EA equal to 1. And if we are going to use the external program memory exclusively, that is, there will be no internal program memory, then we can select that mode by making EA equal to 0, and the range will be from this to this. The external storage is addressed and accessed via input-output ports P0 and P2. In 8051, PSEN is 1, that is, it's active when reading a byte from, it should be 0, that is, it is active when reading a byte from external program memory ROM. The command used to access external ROM is move C A @A plus DPTR. So when we connect PSEN to the ground, then 8051 microcontroller fetches the opcode from the external ROM. But when we connect PSEN to VCC, the status of the PSEN is not activated, since it's an activated low pin. Hence, the program memory is saved in the internal ROM of 8051 itself. So in this way, using PSEN, we can select or deselect the external program memory. So this is the circuit diagram to interface external program ROM with 8051. Here we can see. So all the pins, that's the P0 and P2, are used to address. Then OE and CE, this is the chip enable and the output enable pin, which is connected to PSEN. These pins are defining the control signals. And in this way, so in step 1, connect EA to the ground. Next, step 2, connect the PSEN to CE or OE of the chip. Then port 2, that is P2.0 to P2.7, and A8 to A12 pins of the external ROM. So these are both connected. Now connect ALE to G of 74LS3 73LH to enable it. Now next, connect the OC of 74LS3 73 to ground. Step 6, connect port 0, that is P0.0 to P0.7, which consists of both address and data multiplexed into port 0 to 1D to 8D pins of latch to demultiplex it, and 1Q to 8Q of the latch to this of the external ROM. So in this way connections are made. Step 7, that is connect port 0 to D0 to D7 of the external ROM. So we know that the lower order data bus is connected to the port 0. Now step 8, VPP of external ROM is connected to the VCC. In this way all the connections are made. So it's just to note that 8K into K, it means that the program ROM is organized in a structure that has 8K word space and into 8. That means that each word is 8 bits. This means that 32K into 8 would be a ROM which has the 32K word space and 8 bits per word. Yes, in other words, this means that there are 32,000 locations that are 8-bit wide. The program and the data memory can be of the size 1K into 8, 2K into 8, 4K into 8 and so on. Also, multiple chips of the smaller sizes cascade together to form a chip of larger size. That is, we can connect to these many chips to form one chip. So we can take, if we take 32K into 8, then 2 raised to the power 15, that is 32K, which implies 15 address lines, and into 8 implies 8 data lines. So in this way, to interface this much of memory, we need 15 address lines and 8 data lines. So this is the code. Let's have an idea of it. And similar to this, the code for other interfacing is also written. So let's say we want to move the data stored at the locations 4000H onwards in the external ROM to the location 40H in the internal RAM. So let's see how this is done. So this is the starting of the program using the cellular directive org0000H. Then move DPTR. So the DPTR is loaded with the location where the data is stored. Now R0 is loaded with the int RAM location where we want to save the data. Yes. Now move A. A is accumulator, that is clear. So by loading 00 to accumulator, we are just clearing the accumulator. Move C A comma @ A plus DPTR, that is the syntax to mode data from external ROM to accumulator. So in this way, the data from the external ROM is moved to the accumulator. Now move @ R0, A, that is the value of the accumulator is copied in the location pointed to by R0. Now R0 is increased, INC R0 means R0 is incremented. Now DPTR, that is the data pointer, is also incremented. So by using these two statements, we are incrementing the internal RAM location as well as incrementing the external ROM location. Now compare and jump if not equal, that is C, J and E. If these are not equal to 0, 0, that is if we have not reached the end of the address, then we have to move to REP, that is here. So again this is done. So in this way, the data from the locations 4000H onwards in the external ROM is transferred to the internal ROM locations from 40H onwards. And here the program ends. So, and about the data present at the locations 4000H, this is the data. Using the assembler directive define byte, we have defined 1H, 2H, 0AH, 0F2H, 30H, 5CH, 2AH, 01H, 00 and FFH. So here 0 is the stop bit that we are assuming. So in this way, the RAM location, the external ROM is accessed. Now, data memory space. To access the data memory space, we use the instruction MOVX @DPTR. Connect the read pin, that is pin number 3.7 to output enable of the data ROM and give an active low signal to the chip enable, that is the CE power pin of the data ROM. Here we access the data from the external ROM containing the data and the transferred to the internal RAM. So this is the circuit diagram similar to the one previously shown. Again, this is assembly language program to read 100 bytes of data from the external data ROM located at 1000H and send it to the port 1 of 8051. So here we are starting our program 0000H. This my X data equals 1000H. This is the location where the data is stored externally. Now count EQU 100 to receive all 100 bytes of data. So this is just a counter, we can say. Move DPTR, hash my X data. That is, the instant value is moved to the data pointer. Move R0, hash count, that is instant value of count is moved to the R0. So here DPTR is loaded with 1000H and R0 is loaded with 100. Now MOVX @DPTR, that is, the data is copied from the location pointed to by DPTR to the accumulator. Now here move P1, A, that is the contents of accumulator is moved to the P1. Now DPTR is incremented, that is the next location is reached. Decrement and jump if not 0, that is DJ and Z are not repeat. If this is not reached to 0, then we have to repeat from here. So until all the bytes, 100 bytes of the data are received, this will be executed in the repeat mode. Now here the end of the program is reached. When we talk about the external RAM for data, the RAM memory is called the volatile memory since the cutting of the power to the IC will result in the loss of the data. An improvement of the default RAM is ROM, that is read and write memory, it can be called so, which is in contrast to ROM in which we cannot write any data. So basically there are three types of RAM, that is static RAM, SRAM, NVRAM, that is a non-volatile RAM, dynamic RAM, DRAM. So we are going to interface an SRAM chip, that is static RAM chip. It stands for static RAM access memory, random access memory. The SRAM does not require refreshing in order to keep the data because it's made of flip-flops. So, but the problem with the use of flip-flops for storage is that each cell requires at least 6 transistors to build and the cell holds only 1 bit of data. So this is quite cumbersome, but still we are going to interface static RAM. So how do we access data space? If you want to connect external data memory, that is SRAM, we must connect RD, that is the read pin, and the write pin to the SRAM data memory. In writing the data to the external data RAM, we use the instruction this. We can also use NVRAM as it is the most efficient type of RAM whose memory remains even after the power to the IC is cut off. So what is NVRAM? It stands for non-volatile RAM and is the memory element which combines the best features of both RAM and ROM. Features of NVRAM: the read and the write ability of RAM plus the non-volatility of the ROM. Extremely power efficient SRAM cells built of CMOS. Consists of an internal lithium battery as a backup energy source. Consists of the intelligent control circuitry. So these are the features of the NVRAM. Now, when we talk about this circuit diagram, so we have to connect read to the OE of the external RAM, write to the WE of the external RAM, connect the active low pin of input of NAND gate to the CE of external RAM, where the input of the NAND gates are address lines A15, 14 and 13. We have given 0, 1, 0 to these lines to access the 8000 location of the external RAM. So, in this way, as similar to the previous circuit, we can connect these pins. So, we have to keep it in mind that OE is connected to read and the WE is connected to the write signal, and the decoder logic is made to select the chip. So, this is an assembly language program to send 150 bytes of data or the status of the port to the external RAM located at 6000 H. First of all, to access 6000 H of the data memory, we have to send 0, 1, 1 to A15, 14 and 13 respectively. That is to select the chip. So, now from 0000 H, the data our program is organized. RAM location, that's meant for RAM location equates 6000 H, that is external RAM location is this, count EQU 150, variable count 150D, move DPTR comma at the hash RAM location, move R3 comma hash count, that's the number of the bytes of the data. Now repeat is a label for the instruction move A comma P1. The status of the P1 is copied into accumulator. Now move X at the rate DPTR comma A, that is copy the contents of accumulator to the external RAM. So this represents the external RAM. A call delay, a delay is called, then DPTR is incremented, that is we point to the next location. Decrement and jump if not 0 R3, if R3 is not reached to 0, then this is executed on the repeat mode, and this is the end of the code. So, in this way, the 150 bytes of the data or the status of the port 2 is sent to the external RAM located at 6000 H. So, how to interface external program ROM, data ROM and external RAM with the 8051 in one. So, if we want to connect all these external program, ROM, data ROM and external RAM at once. So, what we will do, so let's say we want to interface 16 KB data RAM, 16 KB program ROM and 16 KB of data RAM, then we will have to follow the following steps. Step 1, calculate the number of address lines required to access 16 KB of data, that is 2 raised to power 14, 16 KB, it's required 14 address lines. So, now we know that we have to use these A0 to A13 as address lines. Now, decide the location of the RAM and the ROM. Here we are going to interface program ROM from 0000H to data RAM to from 8000H. Now, in step 3, we will select the decoder circuit. Here we are going to use this typical decoder, that is 74LS138. We do not need a decoder circuit for program ROM, but we have to connect the decoder to the data ROM and the data RAM. Connect G1 to VCC. You know that this is the chip enable pin, G2A and G2B to the ground. Now connect input A and B to P2.6 to P2.7 respectively and the input C to the ground. We connect external program and the data ROM. For that we can use an AND gate which is with its input being signal from read to access the external data space and PSEN to access the external program space and output to OE of external ROM. Now to interface the external ROM, that's RAM, we connect both RD and write to WE and OE respectively of external ROM. This we all know. So what we have to notice is that the which pins are to be connected to the external ROM and RAM. So this is the interfacing diagram. Here we can see the data RAM, ROM and the program ROM. All three are connected. These are interfaced to 8051. So OE and output enable of both the program and the data roam are connected to the output of the AND gate, and this is connected to read signal. Here WE is connected to write signal. In this way, and using the decoder logic, we are selecting the ICs. So in this way, all the three types of ROMs and RAM are connected to the 8051. So that's all for today. Thank you.